All right, electromagnetic induction, Lenz's law, and yeah, and then analysis of Lenz's law based on the motor, or actually the motor principle, and analyzing motors, I should say. So here we go. Electromagnetism. We know about this, right? We have current carrying conductors. We know that they get a magnetic field and so on. And so the idea was, about the idea of there being reversibility in science, right? So, if current makes a magnetic field, can a magnetic field just make a current, right? And it doesn't automatically just happen. It doesn't happen continually anyways. Like a magnet sitting near a wire isn't continually producing electrical energy. That would just be, it would be against the law of conservation of energy. It just isn't the case. In 1831, Faraday discovered, though, that a moving or changing magnetic field, it's weird they describe moving, but I mean, if an area is ending up with a magnetic field that it didn't have before, that's what they mean by a moving magnetic field. It can produce current in a wire. Now, can, because it depends on angles and so on, right? But that is the idea of electromagnetic induction. And I mentioned that this is going to be looked at in a future lesson. So here we are. But yeah, so he developed the first electric generator. Same design we use to make electricity in general today, except for like solar panels, really, I guess. Everything else you might be familiar with. You boil water, basically turn a turbine, which turns a generator and makes electricity, right? So we'll learn about that, and let's do it. So Faraday conducted 3 different experiments to investigate electromagnetic induction. So moved a wire through jaws of a stationary horseshoe magnet, found that current flowed. Moved a bar magnet in and out of a coil of wire, found that electricity would flow, and moved a coil wire near a magnet. So basically the idea of moving a magnet near a coil or moving a coil near a magnet, of course it wouldn't matter because it's relative motion, right? In all situations, current was induced, but only whenever the magnetic field in the region of the conductor was changing, right? So that's the law of electromagnetic induction. Electromagnetic, I want to just pause quick. Right, hopefully the sound is sound back. But you see here, the magnet goes into the coil, makes a little pulse of current, and then it stops, pulling it out, and it goes the other way, and then it stops, and electrons flow out. Think of it as, of course, when the north is brought in, that induces a north here all of a sudden, and so electricity flows and so on. Okay, so that's the demonstration of that, and so there's the the visualization of this, right? As it's on its way in, it pulses, and on its way out, it's pulsing. Just keep in mind that this right here, like having a current value, is when it's on its way in, and then a current value when it's on its way out, right? It's not just sitting there with electricity flowing. Okay, notice that this is 0 current, right? 0 amps or milliamps or whatever in the middle there. So neat versions of this. There's a light. This is a picture of one that I actually have. There's a video I'm going to show you here, but you see here, this is a magnet, and there's a coil of wire. Literally, you shake this thing back and forth, and as the magnet goes through the coil, it pulses, makes a little bit of electrical energy, and there's a capacitor in there that stores the energy. So you can actually charge it up by shaking it and then flip the switch, and it'll stay on for a little while. Or you can just have the switch on, and as you shake it back and forth, it just makes pulses of light. So let's see. Hopefully this one's pretty quick here. All right, so this is the little light here. So he's talking about here, saying, oh, there's a coil of wire and a magnet and so on. But beginning, as he's shaking it, it just flashes, right? So it's a real thing. So other things to do with this, Faraday's iron ring. He didn't actually have magnets for this. He just made electromagnetism. He did it with electromagnetism, right? So basically, he found that when he turned the circuit on, this would induce a north and a south. Analyze out the appropriate left or right hand rule. And so, because it's a ferromagnetic material, it would induce a north or south over here. In which case, current would flow. He'd find that the current would flow in these wires, and it would make this needle, deflect and so on. This is the kind of apparatus that he actually used to figure this stuff out. So, yeah. So what I described there about how when the electricity flows and it makes a magnetic field, it builds, and then a current. He found that current was induced in the coils when that was happening, and so on. Right. So when you close the switch or open the switch, the needle would twitch and deflect. So this is just what I've been saying. The more turns of a coil, the stronger magnetic field, the more voltage, and so on. That's pretty obvious, but not critical for what we're talking about. So what I do want to focus on, though, what is critical, is the idea of which way electrons flow. And the nicest way to think about it is what's called Lenz's law, which is really based on conservation of energy, as it says. And so an electric current is induced by a changing magnetic field. We know this. This electric current will create its own magnetic field. And Lenz investigated the direction of that magnetic field and found that it would always oppose the change. Okay, so the idea is that if you brought in, say, a north to this ring, and then current gets induced here, so then it makes a magnetic field. If it makes north, that would oppose things and make it harder to push the magnet through, and so it would slow things down. It basically, like, there's friction. Whereas if it made a south, then you push it in, that makes it south, that makes it push in even more, and then that makes it push even more south, and then that makes it important, So the idea is that couldn't be the case, right? Realize if the field were to the right, the magnet would be accelerated by that field that it created, which would make it move more, which would make it accelerate more, which would make it move more, and so on. And that just doesn't make sense, right? So based on the idea of conservation of energy, that there's going to be some energy lost in the system and so on, it can't be amplifying. It can't, give it any push here at all, and it would just build more and more energy as it goes, which if you had a series of rings for a kilometer, just keep building energy the whole time, that just doesn't make sense. Okay. So yeah, it just says that when the magnetic field in the region of a conductor changes, the electron flow that's induced is induced in such a direction that the magnetic field caused by the induced electron flow opposes the magnetic field that caused the induction in the first place. Okay. And as I said, it's really that energy is not building up and coming out of nothing, right? You can actually feel it. If you have a magnet and you're moving it near aluminum or copper, you can actually feel the drag. And I'll show you some videos of the effect of that. It's all the same stuff. There's some redundancy here. So analyze what direction things would be here, right? So you picture this north of a magnet here, and we're going to pull that thing away. That means that a north is leaving this area, and so electron flow would end up being induced, so that it would make a south to try and hold it, right? To try and oppose that change is what would happen, right? So then we can analyze the left-hand, right-hand rule business and figure out which way electron flow would be going. So if we want a north to the left, electron flow would be going, if you point your thumb of your left hand to the left, then electron flow would be going up in the back and down in front, right? That would be the electron flow, not the current, right? Vice versa here, if we're bringing a magnet in, this is going to want to induce a south here again, actually, or south there, that time to oppose the push of the magnet in. Yeah, so same stuff here. The difference here. Which way is the magnet? Which way is the magnet moving? Okay, I get you. So this one here is like, if this is the magnetic field that's there, then which way was the magnet going? So it's working backwards here, right? So you can picture, there must be a south. There's a south here, which means that it was probably trying to push that south in, made a south to oppose that motion. All right, so the analysis of this electric motor that we've talked about before, if it's turned manually, so you take this thing and you move it instead of using electricity to make it move. Well, you think about this is moving, so this end of the coil is moving away from a north, so it's actually going to induce, electron flow is going to induce so that a south would be here, right? And that would oppose that turn, right? So that's the idea of what we would get. And so I think it says over here on this one, oh, this is different. So that's the full analysis there, right? It would be a south to oppose that. So I could put a south in there and so on. And then further analysis could be like, okay, which way would electrons flow be? So if I want this electron, I want the thumb pointed down to the right. That means electron flow is going to be going like this. If you point your thumb down on an angle, away, and your left hand's facing away from you, of course, your fingers are going up in front and down and behind, right? And this is electron flow, like that. So it gives you the power to figure out things like this, right? The engineering design of this, if we had a split ring commutator, then electrons would flow, what was it, up on the front? Yeah, so up on the front in this scenario. And then so up on the front, let me just follow this here. So up on the front like this, right? And then that goes to here and so on. So electrons would be going down through the wire like this and around, so counterclockwise in this thing. Then, you get to the point where you have it switch, right? And then now it's doing that again, but things are hooked up again. So this actually will make pulses of electricity going the same way over and over again, because the coil's completely flipped around. So in the coil itself, electrons are technically going the other way, but they're connected to the other side. So that's the point of that split ring commutator. It would produce DC electricity, and the solid commutator just connected the same way the whole time. Since we know electrons would go up in the front right now, right? And then now up in the front, which is kind of the opposite way, obviously, right? Electrons would go one way, then the other, one way, then the other all the time, right? So they would actually just go back and forth inside of this circuit. So that's making AC, right? So there was actually a big debate at the time between Westinghouse was the main proponent of AC, and Edison was the main proponent of DC. And so it was a big debate as to which was the superior kind of electricity, which one should we use, right? And of course, AC won out. That's what we use. And the reason was because of transformers. So AC, when AC is building and going down automatically all the time, because that's the kind of energy we produce from this, then in Faraday's ring here, I can just use that as an example because this is essentially a transformer, just not changing, because we have a different number of coils. So anyways, the electricity would be going back and forth, making a magnetic field, one way then the other, one way then the other, which is then going to make electron flow in here the opposite way to oppose it, one way then the other, and one way then the other, right? So you end up with electricity being induced, and depending on the number of coils, if you had, say, 3 coils here and 9 there, then you could actually get like 3 times as much voltage. You can transform between voltage and current. Okay, I forget whether we've done transformers yet, or if it's later in this lesson or soon. But it's not super critical. It's not that kind of course, right? We're just the ideas of it. This is another flashlight that does the same thing. There's a little hand crank on this guy, you might have one of these kicking around your house. They're popular at Costco a while back. Usually my students say, oh yeah, I've seen one of those, But anyways, you crank this thing up, and what you're doing is you're turning a motor inside of there, using it as a generator, right? So again, there'd be a battery I think this one actually had batteries, because the one I have of this doesn't really store or charge anymore. So the batteries are probably corroded and dead inside there. Whereas the shaker light still works because it has a capacitor. So it would have been smarter for them to engineer and use a capacitor instead, which we kind of know what capacitors are too. It just, we maybe don't know the official, but you just get 2 parallel plates and you get charge built up on one side than the other, and it just stores energy. And then when you hook it up to a power supply, the electrons can repel away from the negative plate and so on. So our parallel plate stuff is really capacitors. An example of this little eddy current tube, I have one of these. Had a slit cut and it would be different, but you drop a cylinder through that's not magnetic and it drops, due to gravity, as you'd expect. You drop a magnet in there, then you have a north coming in, which is going to induce electrons to flow to make a north opposing it, and it slows down the rate of fall substantially, like a lot. This video here, let me get it going. All right, so here we go. This guy's going to show if you have a magnetic material And you're just dropping it due to gravity. Of course, it's going to do its normal thing. Now, this is a copper pipe, so it's not sticking to it. He drops a pencil through first. You see it goes, should show a full view of this thing so you can see what's really going on, but it falls too fast. You get it. I think there you have a full view now. Boom, just falls, right? And then goes and drops a magnet through. And quite a while later, like it's very easy to get your hand down there in time to catch it. Again, because the north is coming in, so it induces electron flow in the thing, and kind of show an animation of it here somewhere, I think. Yeah. So picture electrons flowing and then making a north that's opposing that, so it literally pushes against it as it's falling. Okay, so yeah, kind of neat. He has different animations or different demonstrations that show this. He drops like a metal ring through, and you can picture what that would feel like, right? See how it's falling. And yep, not bad. All right, here we go. So you can see this ring drops in, and it really slows down, and then and then goes a little bit when there isn't metal in because of the ring and so on, right? So you can picture the feel of that. And I have another video later on about that, and a weird one here. If you just follow the link for this and watch this, but if you get an aluminum disc whirling fast enough, a magnet will actually just enough magnetic field change in the region of the conductor. Now it's because the conductor is moving this time, but I mean, it's still the same thing, right? So a north is coming in into effect in this region of this aluminum over and over and over again every rotation. And that induces electron flow, which makes a magnetic field that opposes this one. So if this is north facing down, it would induce a little north facing up. And if you get it going fast enough, it actually rises up off of the disc, which is pretty cool. So you can actually, if I turn the sound up, you can hear it hitting the. I have sound. Oh, there we go.
Which the magnetism changes for each
you can hear it
surface area point of the aluminum gets higher and higher.
Eventually,
that induces more current.
Which is pretty cool. So, anyways, this is the one I wanted to show you where you can really feel this one. So this is a cart that I have and on a track, and this is just a piece of aluminum, and then that's the magnets that you saw in a previous video where I had the little stick of copper that would roll back and forth in there. So this guy, you can really see I give the cart a push, and when this aluminum gets to where the magnet is, you can really see it slow down. All right, here's a model of electromagnetic braking. So using electromagnetic induction to cause an object to slow down, so like the drop zone at Canada's Wonderland and things like that. So we have an aluminum plate here that's not going to stick to these magnets. We've got a north magnet and a south. And so as this comes in here, there's going to be a new magnetic north and south above and below. And so electrons, that's a new magnetic field. And so you're going to have electron flow in this aluminum so that it makes a north to oppose that new north that happened. So in order to have that, there's basically the electrons in the aluminum are actually going to swirl around like little eddy currents, and they're going to make a north that faces up. Well, that's going to oppose, say the north opposing this north here is going to try and slow it down. And of course, as Lenz's law says, and conservation of energy logically says, the new magnetic field that's produced would oppose the magnetic force, magnetic field that was changing. So try and give the car a push, and it stops and it gets into that area, slows it right down. Right? You can see it. Really works. And again, like I mentioned, it's an application of this is like electromagnetic braking and regenerative braking as well. Vehicles like Teslas and other electric vehicles, they don't really use their brakes a whole lot because they use all that motion energy to regenerate energy in the battery, and that's what slows them down the majority of the time. So I mentioned this earlier. This is the generator principle. Get rid of that. Oh well, I can see through it. So electromagnetic induction, you can analyze it based on the motor principle. So this is where we're picturing the wire itself moving, which is a flow of electrons, right? So we have a flow of electrons up, and we have north to south going left to right. The palm of your left hand should be facing yourself if you extended your finger and thumb that way. So you end up with this magnetic force on electrons out of the page. So literally there's a push on each of those electrons. They are going to flow. It's going to induce an electric current in that, or electron flow in the wire. So because there's a motor force on them, which is weird, right? But that's actually what's pushing the electrons, and that's why EMF and voltage are the same thing, right? So the electromagnetic force is proportional to the magnetic field and the velocity and the length and so on. So there's your familiar formula really from before. And if you look at the units of this stuff, so the proportionality constant has this weird unit if you go back and look it up. So that's, sorry, not the proportionality constant, that's the magnetic field. And then velocity is meters per second, and length is in meters. And then, so we have newtons, where does that work out? Oh, yeah, we have the meters from there. So we have Newton meters and amperes per second. And so we just keep substituting familiar units, right? So the seconds from which part here? Oh, this was amperage is coulombs per second. And so what happened there is an invert and multiply. Okay, so we had coulombs per second in the bottom, but we flip it up and multiply. So seconds are canceling out. So now we have Newton meters per coulomb, which is really, Newton meters is like force times distance. That's work. That's energy per coulomb, right? So like that's voltage, right? That's the concept of voltage, energy per charge. So electromotive force is really the same thing as voltage. And you can even see like the units are the same in the end, which is just, I think, neat, right? This is another example, a neat example too, where we've got superconductors. So this is the superconductor down here, and this is a chunk of a magnet, I believe. Yeah, I have this one listed the wrong way. That's all. I think the superconductor would be this because it's bathing in the liquid nitrogen, and then this is just a neodymium whatever kind of magnet. So if this comes in and wants to impose a north, right, then electron flow would happen here to make a north facing up, and so on. Now, if this was the superconductor and that was the magnet, the analysis would just be the other way around, the way it's drawn there. So let me just pause quick and I'll get that going. All right, so this is the superconductor here. There's a magnet, and it's showing like it's not attracting to it or anything like that right now. So it'd be like putting it near aluminum, right? Like a current would induce, but you'd hardly notice it. But now you try to bring in a north, and current's gonna flow in here to make a north opposing it. And because there's no resistance, that current can just flow completely, unimpeded, making a north the whole time. And it'll actually suspend the magnet, which is just kind of neat. And then, cool examples of this, quantum levitation. So this video shows the same thing, and right? It stays this time, this is the superconductor, and that's magnets. You can tell it's got frost all over it, so it's super cold. But you can make it amazing. As long as it's so the superconductor. And so he's showing like you can just put it wherever you want. We call it quantum locking. Right. And it stays locked. So yeah, so in order for it to go up or down or sideways, the magnetic field would change. Right? Yeah, exactly. And so it's going to make magnetism to oppose that, whereas here, the magnetic field is changing in the region of the conductor by doing that, because it's still just a magnet facing. So it stays there on the X and Y, but rotate. It's kind of neat. Then there's a track that they have where it's magnets all the way along, and so the whole time it's just magnets all the way along. It doesn't matter to the superconductor whether it's first magnet or the second magnet or third. And so, but it can't go sideways because then there wouldn't be a magnetic field near the superconductor. So it's like a little yeah, it can be like this, and it will just go around like this. But yeah, so electromagnetic induction, making that happen. And then the other thing that I'm going to tell you about to help save electric motors in your life is the idea of back voltage or back EMF. Right? Electric motors, you've noticed, are really just a big coil of wire, right? Very little resistance in that. So if electricity is connected, why isn't it a short circuit? Why don't electrons flow like crazy and cause a short circuit? Well, the answer is the spinning of the coils and the electrons in it, of course, is essentially electrons moving in a magnetic field. And so that induces a magnetic field, and so due to the spin, right? And so that makes there be a force, take your left-hand rule and calculate it out. But basically, Lenz's law says that force or electromagnetic force, right, that's created by that spinning actually pushes against the current that was causing things. right? So basically, the more a motor spins, the more back voltage there is on the circuit, and that slows the amount of current down. So when a motor's freely spinning, there's very little current going through it. And then if it slows down, more current manages to go through and make more force on the motor, which then makes it spin faster. But then when it's spinning faster, then more voltage in the opposite direction is induced, right? So this is just how motors work. My electric motors don't use a ton of energy, to be honest. They're super efficient, and the faster they're able to spin, the less current they even use. The trick for this is if a motor jams, there's no spin, there's going to be no back voltage, right? And so current flows without limit, and it's a short circuit. So if you have like a a blender or a mixer you're using in the kitchen, and the whatever you're blending or mixing was too thick and it jams, you got to turn that motor off right away, because otherwise electrons are just flying through the coils of that motor, not being impeded by the spin essentially of it, right? Because it's not spinning. So the motors can really get fried or cooked or burnt out really quickly. So yeah, that might save an electric motor in your life. If it jams, turn it off right away. So yeah, so that is some applications of that. These questions are based on that stuff. So hopefully it works for you, and let me know if you have any questions. All right, thanks for watching, and see you next time.